What up, PCH? So I'm gonna go through pretty much every single problem in the homework from this summative review, and hopefully you're able to do a lot of these. If not, you're gonna find some good help in this video. When I'm looking through here, literally every single question except for this one about thinking about the graph of a logarithmic function, every other question is either solving an exponential equation or solving a logarithmic equation. And so a lot of the steps I go through in a lot of these problems is going to be the exact same. It's just different applications of the exact same process. And so, for example, if we're looking at number one, we have a population of bacteria and it is declining over time. We know an equation that can help us figure some of these things out, represent the situation. And because we're talking about a population, it tells us that explicitly, I want to use my population exponential application equation. And this is something that you will be given on the final and on the summative. However, all you're going to be given is the equation. A equals a sub 0 times e to the RT. You won't be given, it won't tell you hey, this is the population equation. It won't tell you what, a sub 0 even means. That's all stuff that you need to be aware of beforehand, but it will give you the equation. And so the first thing we need to do, obviously, is figure out where the numbers that we are given fit into our equation. And so if our population starts with 5,028 bacteria, that's going to be our initial value, which is a sub 0. And so if it helps you to kind of define your variables, set them up like I do on the side here before you plug them in, I think that's a great thing to do. Or you can go ahead and annotate the actual problem, hey, a sub 0, right above that number, so you know exactly where to plug it in. Well, in 2 hours, the count is 3,106, so after a time of 2 hours, so t is 2, my final or current population of bacteria is 3,106, and I am looking for its rate of decline. This is what I am searching for is r, and because it is a rate of decline, I should expect whenever I'm solving for r, it should be negative. And if it's not, it's probably did something incorrectly. And so when I plug all of these numbers in, I get an equation that looks like this. And what I notice is I'm trying to solve for r, which is a variable in my exponent. Hence, we are trying to solve an exponential equation. And when we were talking about doing this, there are literally two steps. Isolate my base with my exponent, and then rewrite with a log. In order to isolate my base and my exponent, I need to divide both sides by 5,028 because that value is being multiplied times my base to the exponent. And now I'm all ready to rewrite as a log. When I do that, something I notice about this exponential equation is that the base is e, which pushes me to use the natural log, which is this ln that you see here, because the base of a natural log is e. And so that works out great for me. When I rewrite this, I get the natural log of this big fraction equals my exponent, because logs are exponents, so it equals 2r. And in order to get r by itself, I need to divide both sides by 2, so that as an exact answer, r is the natural log of the nasty fraction, all divided by 2. But I want to find an actual value for r, and it's going to be a nasty decimal. I'm going to have to round, but now that this is my final answer, it's okay that I'm rounding now. And so I do want to show you how I'm plugging this into my calculator. I do it kind of step by step. I think it's a lot to do all at one time, and especially with making sure that you have all the correct parentheses because your calculator's picky. I think it's a lot to worry about, so I want to keep it kind of as simple as possible. And so I'm going to start with what is inside my natural log. And you see I've already done that division and found that that is equal to 0.6177, etc., etc. Now I need to take the natural log of that value. And the nice thing is there is no different base, it is the natural log of e. And so I am able to use this natural log button that is on the left hand column of my calculator. So I'm going to press the natural log, and then I want it to use the answer that I just came up with. And so I'm going to go to second, and then down here, this negative button above it has ANS in blue, that is answer. So it's going to take the natural log of my previous answer, so of 0.6177, etc. And I get this negative decimal. And the last thing I need to do is divide it by 2, and I end up getting an R of about, let's see, negative 0.241. So negative 0.241. And that's going to be my answer. That is my R. It is negative, which I was expecting and needed. And that looks great. I found my rate of decline. Let's move on to number 2. All right, because this one is pretty similar to the last question, I'm going to go through this one a little bit quicker. And so you'll kind of see like we're going to follow a lot of the same steps. So as I read the problem, I realized that this is going to be a compound interest problem, so I needed to get my compound interest formula, which again will be given to you on the final and on the summative, but I won't tell you when you should use it. I've also listed, where I'm plugging in different numbers to my formula, and I've gone ahead and done that. In this case, we're solving for t, which again is a variable in my exponent, which means for number 2, once again, we are solving an exponential equation. 2 steps. Get my base and exponent by themselves, rewrite as a log, and solve from there. So you can see my work first in this step, I guess technically like the second step here, the second line of work. I divided 8,000 over to try and get my base and exponent by itself. Also simplified what was going on inside of my base. And then I went ahead and rewrote this as a log. I chose a natural log. It does not matter which one you choose. You could have used the common log, your LOG. It does not matter. But something we noticed here that's different from the problem before is that the base of my log is not, well, I'll say this more specifically. The base of my natural log is not e. And I would also notice, if I had used a common log, the base of my common log is not 10. This causes some issues for us for a couple reasons. In the calculators that a lot of us have, if you go to on, right, you'll see that we have the log and natural log buttons here that we can use only when the base of my common log, which is LOG, is 10, and the base of my natural log, which is LN, is E. That is not the case here, so we cannot use those 2 buttons on our calculator. Some of the calculators, if you go into this button that says math, and on this first list that is math, if you scroll to the bottom, you'll see that there's an option A that says log base. This allows you, when you press enter, to type in whatever base you need or want or have for your log. It does not have to be 10, does not have to be E, it can literally be anything. And so that would allow me to type this into my calculator, no questions asked, things are good. Unfortunately, there are a lot of calculators that we have that do not have that capability, and so we need to do a little bit of extra math to get us to a point where we can actually plug it into the calculator using these 2 buttons that are right here for us on the left side of our calculator. And so let's talk about that right now. We are going to use what is called the change of base formula because, well, we need to change our base back to something that in this case is E. And all we need to do is we're going to turn the natural log of 1.0115, or well, I should say the natural log of base 1.0115 of 2.5 into the natural log of my argument divided by the natural log of my base. What you'll notice now is that we have 2 logs, like it looks a little bit different, but the base of both of these natural logs is now E. This is something I can actually type into my calculator and do good things for. And this is going to be super, super important. Again, if you're in a situation where your base is not E for a natural log and it's not 10 for a common log. Okay, I'll go ahead and show you the rest of my work here. In order to get t by itself, I needed to divide both sides by 4. And so I see that I have kind of this mega fraction. In my numerator, I have my natural log of 2.5 divided by my natural log of 1.0115. All of that divided by 4. You can see here on the left, I've already plugged all of that into my calculator, did it piece by piece. I suggest doing it in the same order that I did, and you end up getting a time of about 20.03 years for number 2. For number 3, I have a function that models the average cost of a new home it wants me to figure out what year will the average cost of a home be $555,000. Well, if this equation models the cost of a new home and they want to know when the cost of a new home is $555,000, I am plugging that in for y on the left side of my equation. And you can see that I've already done that here. Now, when I'm looking at this example, I'm looking at this equation, I am trying to solve for x, of course. And what I notice is that x is in the argument of a log, which means this is our first logarithmic equation that we are trying to solve. Again, 2 steps, very similar to solving an exponential equation. Isolate my log, rewrite as an exponential equation, and then solve from there. You can see my work here. Again, my first step was to try and isolate my log. I needed to subtract my 435,000 over to the left side, divide both sides by 19,664 to get to this step here where my log is isolated. And then I'm in a spot where I can rewrite this as an exponential equation. You can use your chubby hand, do what you need to do, but the base of my natural log is e, so I get e to this nasty fraction, which I plugged into my calculator and got 6.102, etc., etc. You'll notice that when I wrote this as like this decimal in my exponent, I wrote this dot, dot, dot at the end. What that is saying to me, if I'm reading this person's work, and of course it's my work, but assuming it's someone else's, if I'm reading this person's work, what that is telling me is that, hey, like this person plugged this value into their calculator and got some long, nasty decimal. But this dot, dot, dot tells me that there is more there, but they are not rounding. They're not going to sit here and write out 100 decimals or 100 numbers after the decimal place, because that's ridiculous. But this tells me, hey, there's more there. I am not rounding because we're not supposed to round until our final answer. And so I want to see those dot, dot, dots if you decide to do some of this division from the get-go. Now again, it really matters to me that you're able to type this into your calculator, and it's easier said than done. And so I really want you to see what is on the screen of my calculator so you know kind of the process of doing this. Again, I found that my exponent to be this long decimal, and in order to do e to that number, I see that there's a little e here in blue above my division symbol. We need that e. You'll also notice there are these 2 capital letter e's above this like comma apostrophe type deal. That means something completely different. We do not want the capital e's. We want the simple lowercase e above my division symbol, which is in blue. So I'm going to press second divide. It gets me that e. In order to push me up into my exponent, I'm going to press this arrow key. And then I want it to use the decimal I just came up with. And so I'm going to do second negative to get me that answer again. The last answer I previously just came up with. And that is going to say, hey, I'm going to use this entire decimal. I'm not rounding. I don't need to type it in again by hand. I can use what the calculator's already done. Press enter, and I get x to be about 446.98. The key with this question is that 446.98 is not my answer. 446.98 represents the number of years since 2000, because that's what it says x represents. And we need to say, hey, in what year specifically will the average cost of houses be $555,000? And so when I add my x to 2000, I get 2,446.98. That means that in the year 2446, we are not rounding. This decimal puts us within like 98 100ths into the year 2446. That is when the average cost of a home will be $555,000. So no rounding here, keeping whatever number that is in front. Fantastic. Let's move on to number 4. This problem is similar to the first couple, just a different context. We need to use our half-life formula, so I've written that here. And once I'm looking at the problem, I figure out where I'm plugging in each of the numbers, and what I notice in this top equation here in pink, I am solving for t, which is a variable in my exponent. Once again, solving an exponential equation. 2 steps, isolate my base in my exponent, which I have done here in this step, this first one in purple. And then I rewrote as a log. As you scroll down, something you'll notice is that, hey, the base of my common log, my log, is not 10. In this case, it's 1/2. And so in order to be able to put this into my calculator, I needed to use the change of base formula, write the log of my argument divided by the log of my base. And so I have done that here. Plug those things in, need to multiply both sides by 5,730 to get a t of 41.44 years. Well, it tells me that the document should have been 225 years old, but we got this one to be 41 years old, which is obviously, this is obviously a fake. And so that would be the ultimate argument you come up with using your work as your support, your evidence for the reason that this document is a fake. This is a great question, super important question. Again, we are trying to talk about domain, range, some other key features of this function. Well, when I see that I have a log, the first thing I want to kind of decide is to say, hey, is it going to be growth or decay? And that's going to be based on my base. Because my base is bigger than 1, that means I have logarithmic growth. Logarithmic growth. And I know what that looks like on a graph, but it's kind of going to be decided by where my asymptote is. When I'm talking about logarithmic functions, I always have a vertical asymptote. And so when it's looking at at part D, what is the equation of my asymptote? Well, vertical lines are always x equals. So I know that for a fact. It's going to be x equals. And that is going to come from whatever number is being added or subtracted inside of the parentheses with my x in the case of a logarithmic function. And so because it's x minus 2, based on what we know about transformations, that means our graph has been shifted to the right 2. And so I know that my vertical asymptote is at x equals positive 2 because it has been shifted to the right. And then I know what the basic shape of a logarithmic growth function looks like. It looks something like this. And so I can use this quick sketch of my graph to help me come up with the answers to A, B, and C. And so I'm thinking about the y-intercept, right? It does not cross my y-axis at all. So I'm going to say, hey, there are none. Nice. When I'm talking about domain, well, it's not going to the left of my vertical asymptote at all. And so it is literally going to be from my vertical asymptote, which is positive 2, not included because my graph will never touch my vertical asymptote. It will only get super, super close. And then it is going to the right forever towards positive infinity. That is my domain, from 2 to positive infinity. When I'm thinking about the range of a logarithmic function, it will always be all real numbers, which is negative infinity to positive infinity. It doesn't matter if it's been shifted up or down, left or right. My range will always be the same for logarithmic functions, all real numbers. Fantastic. Let's move on to 6, 7, and 8. Which are all solving logarithmic equations. Literally following the exact same steps we were doing earlier for solving a logarithmic equation, but this time it looks a little bit different, right? We want to isolate our log and then rewrite as an exponential equation. Well, here, if I'm looking at number 6, I have 3 different logs. That is no bueno. I need those to all be condensed into a single log, and I can do that because each of my logs has the same base. And so, according to my log properties, I say, hey, if I have logs that are being added together, right, if those logs are positive out front, and I notice that that is the case for these first 2 logs, when I condense them into a single log, both of those arguments are going to be multiplied together in the numerator of my new argument. X plus 1 times x plus 7. I see that happening here. Because this third log has a negative out front, that means it's going to be division, which throws that argument of x into the denominator of my new argument. We practiced this. We felt good about it. You can see how I condensed these 3 logs into 1 log, paying attention to the sign out front of each of them that is telling me whether or not that argument is going in the numerator or denominator of my new argument. I have 1 log. It is isolated. Now I want to rewrite as an exponential equation. Okay, when I rewrite it as an exponential equation, I can use my chubby hand. 4 to the 2nd power is equal to my argument, and I have done that here. Once I continue to simplify, I notice that I'm trying to solve a quadratic equation because the biggest exponent I see on my x is a 2. In order to solve a quadratic equation, we talked about this. I first need to set everything equal to 0, which I have done, and when that is the case, that allows me to then factor and solve for x. And when I do that, I get x equals positive 7 and positive 1. We are not done here, and I cannot stress this enough. Whenever we are trying to solve a logarithmic equation, and we see that eventually we end up having to solve some sort of quadratic to get to x, right? Like we did here, x squared minus 8x plus 7. I need to make sure that I am plugging these values back in for x into my original equation. So what they gave me, this one up here that is not condensed, and I need to make sure that I am not getting any negative arguments. And so I've included that note here again. Check for negative arguments in the original. I'm going to plug in both of these x's and go ahead and see that. We'll start with positive 7. When I plug in a positive 7 for x into my original equations, what I notice is that this first argument, 7 plus 1 gives me 8, 7 plus 7 gives me 14, 7. All of those are positive numbers. We don't have any negative arguments, so I'm like, hey, that works for me. I like this solution. I can do the same thing with a positive 1 when I plug that in for x. 1 plus 1 is 2, 1 plus 7 is 8, and then 1 is 1. Once again, no negative arguments. I like that, and so I end up having both of these as my solutions. Now that will not always be the case. For example, in number 7. I'm looking at my work for number 7. I've already shown everything here. I had to condense these two logs into one log, rewrite as an exponential, and continue to solve from there. Once again, ending up having to solve a quadratic to get to x, to the point where I get x equals 3 and x equals negative 2. But once again, I need to make sure I'm checking these in the original to check for negative arguments. When I plug in a positive 3, that checked out, it looked good. However, when I plugged in a negative 2, in this first argument, I got 2 times negative 2, which is negative 4, minus 1 gives me an argument of negative 5. That is negative. That is not good. We do not like that. I need to not include that answer as a part of my solution because it is extraneous, and so I have crossed it out. My only solution for number 7 is x equals 3. And I'm going to go ahead and show you my work for number 8 as well. Same sort of thing. I have 2 logs. I need to be able to condense them, so I moved the log on the right side of my equation to the left, condensed, rewrote, solved for x, checked for negative arguments, and ended up finding that only x equals 4 is a valid solution for me. For the rest of the problems, again, following the same sort of steps, so I'm just going to kind of show you my work, demonstrate, for number 9, I figured out where my numbers are going in my equation, recognize that I'm solving for k, which is a variable in my exponent, following the exact same steps I have been this entire assignment. And you can see my work here. I got a k of about negative 0.111. And part B is super similar, just solving for t instead of k this time. For number 10, on this one's super straightforward. It's not in the context of like a real world situation. It's just, hey, here's the equation, solve for v, which is a variable in my exponent. I did that, got my base and exponent by itself, rewrote as a log. Same 2 steps. It does not change. It just does not change. You're able to plug that into your calculator to get your v value. For number 11, I do want to stop on this one for a second and say, hey, I know this looks like it's going to be a compound interest problem, but one key thing we mentioned like a little bit when we were talking about these applications was that whenever we have something being compounded continuously, we are going to use the population application formula. Because there's not really anything we could plug in for n, if it's compounded continuously, that would be like infinity, and that's not really something we can work with in our equation. So we're going to use the population formula, which I've done here, and you're able to solve for t following the same steps we had once you start with that equation. Lastly, number 12, this is nice because what we notice is that, yes, we are using an exponential equation. However, we're actually solving for our initial value, which is a coefficient out front of our base and exponent. We don't have to do anything too fancy. We don't have to solve using logs because we're not solving for a variable in our exponent in number 12. And so you can see my work for this question. I got 113.5 grams. All right, and that is this assignment, me going through it. You have access to the key. Continue to check your work, ask questions, make sure you understand these processes. Nice work, PCH.